the standard deviation, the expectation is 0. So f double prime at 1 is 0. This means it's a fair coin. And if you take the second derivative, you get 1/2 times 1 minus x to the minus 2. Then you plug in, sorry. And now I need 1 minus. Okay, you take a second. Yeah, that's right. That's right. Second derivative. Yeah, that's so taking f prime of 1 squared minus f double prime of 1. So, so the expectation is the standard deviation at sigma is 1/4. Now you toss the coin many times, n times. And you have something resembling the famous bell curve. You draw a histogram with a binomial coefficient. So if you do it n times, this is the probability generating function if you do it n times, and n could be big. If n is big, very soon you get something in bell curve. So you have the random variable, the number of dollars, that's x sub n, number of dollars after n tosses. After n throws. So by the linearity of expectation, it's also 0. Your expected gain is 0. You may win, you may lose. And also, the standard deviation is n by the linearity of this. Now let's look at the normalized standard, normalized gain. So the expectation of course is 0 for x sub n. But then you consider the normalized random variable. You define it by the standard deviation. By sigma, by this case n. Now if you plot this probability generating function, you get the famous Gaussian curve. This is the central limit theorem. And my computer has basically a one-line proof of this. This is a warm-up. Let me tell you how it does it. It uses the method of moments. For every random variable, we can define the moments m sub r of x to be, assuming that the expectation is 0, the expectation of x to the power r. It's more convenient to use the so-called factorial moment. But this means the falling factorial, x times x minus 1 times x minus 2 times dot 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 x minus r plus 1. So I like to compute x sub n, this sub n, sorry, or x sub n for now, not this sub n, x sub n. How can the computer compute it? Very easily, using generating functions. The probability generating function for this is n, is this. So you write this as a Taylor expansion with respect to 1. Or it's more easy to write x equals 1 plus z and then have a Maclaurin expansion. So you have 1 plus z plus 1 plus z quantity to the negative 1 over 2 to the power n. You can do it for any, by the way, for any atomic. It doesn't have to be a coin or fair coin. Could be a die. You can play a die, could be any phase die, could be any probability distribution. The same technique works. Is that for the sake of illustration? I'm doing it. And then you write it as the Taylor expansion is take to 0 because of Maclaurin expansion. And this is exactly, it's an exercise f of r n of r factorial z to the power r. R goes from 0 to infinity. And with maple now, with this, you can easily guess these guys. You put this symbolically. With this symbolically, you do the Taylor expansion. It's a command called Taylor. So you enter this expansion with n, you do Taylor, and you do the first 10 coefficients, and it spits out polynomial expressions, explicit. They give you a theorem. In the old days, Gauss had to work to get f sub 20 of n exactly. But nowadays with maple, you can get a table of these polynomials, and obviously these are polynomials. If you explain the mononomial theorem, then before you know it, you see a pattern. You see right away that this is a polynomial. So f, you have two types, even and odd. So these things that easily come out of maple or any computer algebra system has a nice. You cannot, for any specific r, up to r equals 1,000,000 or maybe 1,000, you can find the full polynomial. It's a polynomial of degree r over 2 in n. But there is no known, and probably does not exist, a closed form for f of 2Rn in terms of r alone. But for the asymptotics, we only need the leading terms. So if you glance at the output, you get a beautiful, you can easily conjecture the leading terms. It's 2r factorial, it just tells you. And the computers can also do it automatically. You can teach the computer how to guess and how to find such a thing. This is the leading term. And it's very easy also for the computer automatically. You can do it by glancing it, but you can also do it completely automatically, do the guessing, the next terms. To the r factorial to the power r times r minus 1 times 2r minus 1 over 2 times n to the power minus 1. And for each specific things, n to the power r minus 2, n to the power minus 3, you can guess such an expression completely automatically. So if you want the asymptotics up to 10 terms, you can easily guess. And something similarly for the odd factorial moments. Oh, by the way, once you have explicit formulas for the so-called factorial moments, you can get explicit formulas for the regular moments using Stirling numbers. And also the computer, my program, does it completely automatically to find this. But right now, let's stick to factorial moments. For the asymptotics, that's enough. The leading terms is the same. And for the odd moments, you get a completely explicit formula. So the computer guesses. Minus r times 1 plus 2r plus beautiful conjecture that the computer can test up to r equals 1,000,000. Well, maybe 10,000. But this is not a proof. Yes, it is. I claim that this is already a proof. But to convince the skeptic, here is the formal proof of this. You look at this expression. This, sorry, where is it? Here. Let's call this contraption capital F of NG. Obviously, we have the following simple recursion. F of n plus 1z equals 1 plus z plus 1 plus z to the minus 1 over 2 times f sub n to the power z. But by definition of the factorial moments, right here, we have the following. Sigma f sub r of n plus 1 over r factorial times z to the power r. R goes from 0 to infinity equals, and now I hope you know you can do it in your head, not even another computer. 1 plus z, this is 1 minus